Okay, so the last talk of the session will be given by Elakhras from EPFL. Aya is a third-year PhD student in the Processor Architecture Lab at EPFL, working under the supervision of Paolo Ienne. She graduated from the American University in Cairo with a BSc degree in computer engineering in 2020 and started her PhD in the same year. Her research interests include electronic design automation, Dataflow architectures, and compilers. Her current research focuses on optimizing circuits generated for dynamically scheduled high-level synthesis.
Thanks for the intro. I hope I'm hearable. So hello, everyone. So let's get started. Just like the previous presentation, this presentation is also about dynamically scheduled high-level synthesis, but our main focus here on the process of Dataflow circuit generation. And let me start by explaining a bit the operation of Dataflow circuits. They are composed of Dataflow components that communicate through a handshake protocol that transfers data upon the validity of the data and upon the readiness of the receiver. And so in those circuits, data transfer can be abstracted as a token delivery between the producer and the consumer. And so the process of Dataflow circuit generation can be thought of as a question of how to deliver tokens between data-dependent components. To answer this question, we rely on two pieces of information. The first is the control flow graph, which is composed of basic blocks that separate code based on control flow. And the second is the data flow graph that captures the data dependence. For the rest of the presentation, I'll focus on delivering the data held in the variable val. And the circuit you see to the right here is doing the delivery of the data in the variable val. It is a product of our recent work called fast token delivery that delivers the data with the minimum possible control flow. So as I said, what's so special about this circuit is that it honors the data dependencies while holding the minimum possible control flow. And in doing so, it exploits levels of parallelism that were not achievable by prior solutions. So this circuit nicely honors the data dependencies, but unfortunately, it does not honor the memory dependencies. So as you can see here, there are two memory operations, load B and store B, and naturally, data flow circuits do not honor memory dependencies because they have out-of-order execution. And so, for instance, in this example, nothing in this circuit prevents the green load that corresponds to the I equals 1 iteration from happening before the blue store that corresponds to the I equals 0 iteration. And of course, this is wrong. Previous work proposed the smart solution to this problem by inserting the load store queue to reorder those out-of-order memory accesses. And the operation of the load store queue is summarized in the given 4 steps. And in the context of our data flow circuit, the most challenging of those 4 steps is the first step, which is about allocating operations in the load store queue in order. And the reason why it is challenging in our context is because in our data flow circuits, we have no sense of order at all. So how could we allocate in order? And our work answers this question. So now that I gave a brief, I defined our context, let's elaborate further on the problem that we're trying to solve. So given this data path, this circuitry that honors the data dependencies, as we have seen, it does not honor the memory dependencies, and we need to interface it with the load store queue to do so. Interfacing it with the load store queue requires some extra circuitry, again, for the in-order allocation. We are not the first to tackle this problem. There exists previous work that proposed the correct solution for this problem. However, I must say that the proposed solution is very conservative, as you will see in a minute. And let me say what the solution is about. The solution says, why don't we construct an in-ordered network that strictly mimics the entire sequential control flow? What does this mean? Let's see a simulation. So we have a token, our data abstraction. It starts in basic block 1. It waits for the computation of the condition C1 of the basic block 1. And then, based on the condition, it either goes to basic block 2 or to basic block 3. Here it comes to basic block 2. Notice in the bottom left here, you have the schedule of the allocations happening. In basic block 1, we have 1 memory operation, so we do 1 allocation. In basic block 2, we have no allocations. And then it continues, moves to basic block 4, computes the condition C4, and does the allocation of store B. And then it repeats again, starts a new iteration, the green iteration of the loop, and does a new allocation. In the meantime, while this is happening, the data path circuitry to the right is also executing. The operations in it are happening. And as you can see here, a new iteration, the green iteration, can start at best 4 cycles after the first iteration. And let me give you a hint. The bottleneck here is the allocation circuitry. And to see why this is the case, let's imagine hypothetically that someone gave us a guarantee that we have no memory hazards and we can get rid of the low store queue completely. So gray out the circuit and we have only the data path. Nothing in this data path prevents you from starting a new iteration immediately 1 cycle after the previous iteration. And so obviously the allocation network is the bottleneck here. And this triggered us to think, I mean, there must be a better solution for this problem. And in fact, there is. Remember the execution timeline of the allocation, there were some gaps due to the fact that you don't do any allocations in basic block 2, for instance. So why don't we move our allocations to happen earlier? Why don't we allocate as early as possible? Go straight to the queue. And in doing so, you can start the green iteration at best every 2 cycles, which is 2x better than the previously proposed solution. And this is exactly what we would like to do. And the intuition behind this idea, how could we do so, is, as you can see in the circuit, I grayed out some components that are redundant. I don't need to wait for the condition C1 to be computed. I don't need to wait for C2. I can move immediately from allocating load B in basic block 1 to allocating store B in basic block 4 immediately. And so the idea is to, instead of mimicking the entire sequential control flow, to mimic exclusively the minimum control flow that is needed for you to have the right order. So here you go, directly from BB1 straight to BB4. And so let me elaborate how we systematically do this. This is our straight to the queue solution. The idea is as follows. In this example, the minimum thing required is that you allocate the store B immediately after the allocation of load B. So you can think of it as a producer-consumer relationship. If I have some producer that tells me, hey, I have successfully allocated the load B, and it's time now, you're safe to allocate the store B. So if we are able to represent the memory dependencies as fake data dependencies, we can do the trick of having the right order. And then after adding those fake producer and consumers, we can run our fast token delivery algorithm that generates the circuits honoring the minimum possible control flow. And with this, we can achieve our desired performance of starting a new iteration every 2 cycles. And so the question is how to systematically position those new fake producers and consumers. And the answer is simple. Let's start from the code we have and let's step by step add parts to the code we have. And we are guided by 2 main rules. The first rule is that the allocation of a memory operation should happen whenever the control flow arrives to this memory operation. And this is equivalent to saying, let's add a variable in the same basic block as my operation. And the second rule is that I need to allocate a memory operation only when all the memory operations that I am memory dependent on were successfully allocated. And this is where you have the producer-consumer relationship requirement. So if you add some producer and consumer to honor this memory dependency as a data dependency, you do the trick. And with this, we add a pseudo function called allocate load and allocate store to honor this dependency and respect the order. And since those functions honor the order, we can use them to manage the allocation to the load store queue in order. And so the next question is how to implement those pseudo functions. We have a very simple answer. For the 2 pseudo functions, we implement them with one component called sequentializer, or sec in short. Since memory operations can have an arbitrary number of memory operations that they are memory dependent on, so this sec component can have an arbitrary number of inputs. So we insert a synchronizer at the input to synchronize all of the coming inputs. And then we insert a fork which replicates the input so that you pass one token to the load store queue to manage the allocation and another token to honor the data dependency next to the consumer. And finally, we add a register which introduces a 1 cycle latency to make sure that you don't have 2 allocations happening in 1 cycle. And so we have this representation as an intermediate representation, and we pass it to our fast token delivery circuit generation methodology. And the fast token delivery generates the circuit here at the bottom. It implements those pseudo functions as a stack, and it respects the minimum control flow in doing so. And in doing so, it generates the nice execution timeline that we desired in the beginning. And now it's the time to see how we evaluated and implemented our methodology. We implemented our methodology as an LLVM path and integrated it into dynamically scheduled high-level synthesis tool. We used the entire infrastructure of Dynamatic as is and varied just the 2 yellow blocks I'm showing here. For the load store queue allocation, we used our approach, and for the circuit generation, we used the fast token delivery. We evaluated our methodology against 2 baseline implementations. The first is having a conservative allocation methodology with the fast token delivery. And the second is having a conservative allocation methodology with a conservative token delivery that existed before in Dynamically. So we normalized our results against the entirely conservative approach. And here the graph shows the execution timeline and the number of flip-flops. The diamond-shaped points, each one corresponds to 1 benchmark. They are the result of the fast token delivery plus the conservative allocation. And as you can see here, the effect of the fast token delivery is clear because your execution time and the number of flip-flops is improving. And then the blue, the square-shaped point correspond to the fast token delivery plus the straight allocation, and it shows the effect of our approach. Our approach basically reveals the full potential of the fast token delivery methodology. And now let's explain a bit of the benchmarks. The best result we got in one benchmark called the get-tang. It's inspired from the tangent computation. And the reason why it gains here is because it has an improvement in the initiation interval. The second set of results are mainly loop dominated, and the reason why we gain is if you look at the execution timeline on the top, in the conservative approach, you have to wait for the allocations to happen in the sequential control flow. So you have to wait for basic block 1 to finish its iterations and basic block 3 to finish its iterations, whereas in our approach, we can allocate immediately. And finally, other benchmarks have a very simple control structure, and in simple control structures, our approach results in almost the same allocation network. And with this, I conclude my talk. We were able to solve the load store queue allocation problem, and our results vary to dominate prior solutions. Our artifacts are publicly available, and they'll be available in the poster session for discussion, for questions. I'll be happy to have everyone. Thank you.